In this presentation, we are going to talk about hydrostatics. Among solid, liquid and gas, only solid maintains a fixed shape and a fixed volume, even if a large external force is applied to it. On the other hand, both liquid and gas have the ability to flow under the action of external force. Hence, liquids and gases are called fluids. A fluid which is incompressible is called ideal fluid. This means if a force is applied on ideal fluid, there will be no change in its volume. In hydrostatics, we study the properties of fluid at rest. In a liquid at rest, the forces exerted by the liquid are always perpendicular to the surfaces in contact with the liquid. The total perpendicular force exerted by a liquid at rest on a surface in contact with it is called thrust of the liquid on that surface. Thrust exerted on unit area is defined as pressure. In a liquid at rest, pressure at a given point is exerted equally in all directions. Therefore, it makes no sense to associate direction with pressure. This is primarily the reason for having pressure as a scalar quantity, though force is a vector quantity. Now let's obtain an expression for pressure exerted by a liquid column. If the density of the liquid be rho, then a liquid column of height h will exert pressure P equal to h rho g on every point below the liquid column. Here, g stands for the acceleration due to gravity. As both rho and g are constant for a liquid column, this means pressure is directly proportional to height of the liquid column. At next, let's discuss Pascal's law. Pascal's law states that an increase in pressure at one point of the enclosed liquid at rest is transmitted equally to every point of the liquid and to the walls of the container, provided the effect of gravity is neglected. Based on Pascal's law, applications such as hydraulic lift and brakes are made. The next key term is buoyant force. The upward force acting on a body partially or wholly immersed in a fluid is called buoyant force. Archimedes' principle helps us to quantify buoyant force. According to Archimedes' principle, when an object is partially or wholly immersed in a liquid, the buoyant force acting on the body is equal to the weight of the liquid displaced by the object. Proof of Archimedes' principle based on a fully immersed cylindrical object is shown here. Based on buoyant force, it can be found whether an object will float or sink when placed into a liquid. When weight of an object is more than the buoyant force, the object will sink. When weight of an object is less than the buoyant force, the object will float. In case weight of the object is equal to the buoyant force, the object floats within the liquid at any depth below the free surface of the liquid. These three conditions together termed as principle of flotation. At next, we have surface tension. Surface tension is the property of liquid by virtue of which its free surface behaves like a stretched membrane under tension and tries to occupy area as small as possible. Surface tension of a liquid is measured as the force per unit length in the plane of the liquid surface acting at right angles on each side of the imaginary line drawn on the liquid surface, that is T equal to F by L. The work done against the force of the surface tension per unit area in increasing the surface area of the liquid at constant temperature is called surface energy of the liquid, that is sigma equal to W by delta A. Now surface tension can also be defined in terms of surface energy. If we stretch a membrane as per illustration, the work done against the surface tension is W equal to 2TLX, and as per the definition of surface energy, sigma equal to W by A, which makes sigma is equal to T. Therefore, surface tension can also be quantified as the work done against the force of surface tension at constant temperature to increase the surface area of the liquid by unit area. At next, we discuss excess pressure. For plain liquid surface, pressure on liquid side is equal to the pressure on the vapor side. For curved liquid surfaces, pressure on its concave side is greater than the pressure on its convex side. Here, the expressions for excess pressure for three different cases are shown. For air bubble in a liquid, excess pressure is 2T by R. For soap bubble, excess pressure is 4T by R. For liquid drop, excess pressure is 2T by R. When a liquid surface touches a solid surface, the shape of the liquid surface near the contact is generally curved. This effect is due to the presence of cohesive forces and adhesive forces. The angle of contact between a liquid and a solid is defined as the angle which the tangent to the liquid surface at the point of contact makes with the solid surface inside the liquid. Another interesting phenomena related to surface tension is capillary rise. Capillary rise occurs to balance the excess pressure of liquid on the concave side of the liquid-air interface. The expression for capillary rise is H equal to 2T cos theta by R rho g. In case H is less than the height of the tube, in that case theta will adjust itself so that the principle of conservation of energy is not violated. To summarize, in this presentation, we have discussed the foundations of hydrostatics. We have discussed Pascal's law, buoyant force, Archimedes' principle, principle of flotation, concepts of surface tension and surface energy, excess pressure, and capillary rise.